Hi, I'm John Doherty, and this video is about optimization under uncertainty using data space inversion. This video will bring together a number of concepts, but let's start off simple, define some of the terminology that we'll use, and then get a little bit more complicated as we go along. So let's start off with decision optimization. And the terminology we'll use will pertain to groundwater management, but optimization itself, of course, has been a field of activity that's been around for a long time, and a lot of algorithms have been developed to solve constraint minimization problems of the type we'll talk about in many different disciplines. But what we're looking at is we want to achieve something. We want to manage a groundwater system in a way that certain objectives are met. And we want to minimize the cost of performing that management, but we still want to achieve those objectives. So we decide on a course of management action, and we ask ourselves, what's going to happen if I do this or that? So what's going to happen will normally be calculated by a groundwater model. For example, we might specify that management is successful if heads are maintained above a certain level near a groundwater dependent ecosystem. We might specify that management is successful if a dewatering system is such that inflow into a mining pit is kept below a certain level, or that contaminant is contained by pumping, or that pumping removes all contaminant from the groundwater system by a certain date. These are called constraints. These are the things we want to achieve as an outcome of management. Now, whatever we do is going to cost. And in the groundwater context, those costs will be drilling costs, pumping costs, pipelines, disposal, and other costs. These are just examples. They'll be calculated by a cost model. And then the levers, the management levers, the things that we choose that'll determine how much things costs, will be things like how many wells we drill, where we place those wells, how much we pump from those wells. These are referred to as decision variables. These are the things that an optimizer program, an optimization program, has to minimize subject to the constraint that we achieve our management goals. So that's how constrained minimization works. Minimize costs subject to the constraint that we achieve certain management objectives. So, looking at it a little bit more algorithmically, some way or another a selection is made of the decision variables. A cost model then works out how much it costs, how much the choice of those decision variables costs. A groundwater model calculates what the management outcome of those decision variables is going to be, the states and fluxes. Then some kind of optimization software is going to look at the cost, try to minimize it. It's going to look at the outcomes of the groundwater model and compare them with the system of the objectives, the management objectives that we want to achieve, and then try to reduce those costs constrained by the fact that we want to achieve our management objectives. This is constrained minimization. And this is the task of this kind of optimization software. Now, as I've said, problems of this kind are solved all the time, everywhere, and have been done so for a long time. And there's some quite clever software around, like based on principles like sequential linear programming, sequential quadratic program, which can solve problems like this quite efficiently if the relationship between decision variables and cost, and the relationship between decision variables and model outcomes or management outcomes is fairly linear. These can solve such a problem without too much trouble, without too many runs of the groundwater model. If, however, these relationships are very nonlinear, things start to get a bit more complicated. But there are other tools that we can use, so-called global optimizers. These can work in much more in worse situations where it might be hard to find the point at which cost is minimized subject to the constraints we want. If the relationship between decision variables and costs and model outputs is highly nonlinear, then we may have no choice but to use so-called global optimizers, of which there are many around, all with different strengths and weaknesses. But the thing about global optimizers is that they generally require many more model runs to find that constrained minimum than these other methods that rely on a more linear or approximately linear relationship between decision variables and model outputs. Now, before finishing this introductory part, I'll just briefly discuss something which I won't really talk about anymore in this video, but it's worth mentioning just once. And this is something many of you will have heard of. It's called the Pareto front. So on the horizontal axis, I'm going to plot the extent to which one of our constraints is violated. And on the vertical axis, I'm going to plot cost. So I choose a set of decision variables. And for one particular set of decision variables, perhaps the situation can be defined by that red dot. Low cost, but serious violations of our constraint. Not good. Perhaps for another set of decision variables, the cost is very high, but all my constraints are respected. There's a trade-off implied here, and that trade-off can be defined by a thing called a Pareto front. Now, the Pareto front is a locus of points. There is no set of decision variables which can put us on this side of the Pareto front. The Pareto front, any point on the Pareto front, it is not possible to reduce the cost without increasing the extent to which our constraints are violated. However, to the top and the right of the Pareto front, decision variables are such that we can reduce the cost and reduce the extent to which constraints are violated at the same time, not on the Pareto front. So this defines a kind of a trade-off curve, and sometimes being able to see this front can assist in the decision-making process. A nice byproduct of using global optimizers is that without too much change to the global optimization algorithm, it is possible to define or roughly outline this Pareto front. So global optimizers will come up with lots of different decision variables, and the model is run, the cost is accumulated, and we can see where we lie in this cost constraint violation space. Over time, the global optimizer does its job, and we may be able to define something approaching the Pareto front. And sometimes being able to view this front can help us make the decision. We can decide where we'd like to be on this trade-off curve, what we're prepared to sacrifice in terms of not quite meeting our management objectives if we can reduce the cost a little bit. But that's all I'll say about the Pareto front in this video, and that provides something of an introduction to the concepts of optimization, of which we're now going to make a little bit more complicated as we talk about optimization under uncertainty. So here we've got our optimization software, and it's selected a set of decision variables. Calculating the cost is fairly straightforward, and a groundwater model is used to calculate the outcomes of that choice of decision variables, the states and fluxes. But we know that whatever is calculated by a groundwater model is uncertain. We know that even if the model's calibrated, there's still uncertainty, and often a lot of uncertainty associated with its predictions. So that really needs to be taken into account as we solve this constrained minimization problem. So we know that there's many different ways to fit a calibration data set. we know that it's possible to have many different parameter fields, all of which are in accordance with the prior probability distribution of hydraulic properties, all of which fit the data fairly well, but with considerable variability between them that may cause certain decision-pertinent model outcomes to have a lot of uncertainty. So when we use the groundwater model to calculate the outcome of the choice of these decision variables, should we use this parameter field, which may be a sample of the posterior probability distribution of the hydraulic properties? Should we use this sample, this sample, this sample, this? Well, probably we should use lots. Many samples of the posterior probability distribution of model parameters. Then run the groundwater model many times. And then instead of looking at any one output, we look at them all. And if we're particularly risk averse, we might say, I'm going to choose the most pessimistic of these states and fluxes, and that's going to be my constraint in this optimization problem, this minimization under constraint problem that I'm solving. I want to be very sure that there are no circumstances for which I violate the constraints. Or we could say, no, that's being perhaps just a little bit too risk averse. I might have, for example, 100 parameter fields here, 100 samples of the posterior probability distribution of model parameters. And I might decide to be risk averse but not entirely risk averse, and I'm willing to take perhaps a 10% chance that management won't be successful. So I might run the model 100 times and then select the 90th most pessimistic set of outcomes and use them as my constraints. So the task of the optimizer then is to minimize cost and respect this constraint as defined probabilistically in this way. Of course, this is going to be a more costly exercise in respecting constraints defined in this way, but if I want to be sure that management won't fail, then that's the cost I have to pay. But in the meantime, I've got another cost to pay, and that's a numerical cost to pay. Every time that this optimization software decides to test a new set of decision variables, the model that it has to run is actually many different instances of the groundwater model. And if the groundwater model takes a long time to run, this can become extremely numerically costly. And there's another cost to be added to this. Prior to doing this, I have to have obtained all these samples of the posterior probability distribution of model parameters. And I have to be sure that these are good samples of the posterior probability distribution of model parameters. This is not as easy as it sounds. Have I sampled the posterior probability distribution properly? Are the samples, do they give an illusion of that the uncertainties are too wide or not wide enough? We can never be sure of that, so regardless of how we do it, obtaining these samples of the posterior probability distribution of parameters is another numerically intensive task that precedes the optimization under uncertainty task with which we are now confronted. Put it all together and we've got a very large numerical burden. So optimization under uncertainty requires that the groundwater model be run many times. Now there are some clever algorithms that allow us to reduce perhaps the number of samples that we use as time goes on, but nevertheless we can never get away from the fact that each time a set of decision variables is chosen, the groundwater model has to be run many times based on samples of the posterior probability distribution of parameters which we believe are credible. Because this is now quite a nonlinear optimization problem, because it's probabilistic, we have to use a global optimizer. And as I said a little while ago, that requires a lot of model runs. So for all those reasons, the fact that our model is now many models, that we have to use a global optimizer, that we have to precede this process by obtaining samples of the hydraulic property distribution, the posterior probability distribution of model parameters that I trust. There's model runs, and it's extremely numerically intensive. And that is why optimization under uncertainty is still not done very often in our industry. So that sets the scene for looking at a faster way to achieve this important goal. But before we do that, let's say a few words about data space inversion, or DSI. Now, the beauty of DSI is its extreme numerical efficiency. Based on only a few hundred runs of a complex model, it gives us the ability to make predictions of future system behavior, which are actually samples of the posterior probability distribution of that behavior. And we can do this without actually having to calibrate or history match the complex model. Now I'm going to show you a few details about how this works, but see other GMDSI videos for full details. The process starts off by generating a number of samples, say a few hundred, say 500, samples of the prior probability distribution of model parameters. Now, this prior probability distribution can be complex. The parameter fields can be categorical. We don't have to adjust them. So they could be generated by a modern-day geostatistical field generator. So they can be as complex as the structural complexity of the complex model. So we generate, say, 500 realizations of the prior parameter probability distribution, run it through the model, run the model over the past and into the future. There's certain aspects of the future that we're particularly interested in, predictions of management interest. There's certain aspects of the past that we're particularly interested in. These are model outputs that correspond to observations of fluxes and states, things that comprise the history matching data set. So let's just focus on those particular set of model outputs, those that correspond to the measured past, those that correspond to the managed future. Let's put the model aside now for the moment. Let's put the field data aside now for a moment. Optionally, we can do a normal score transformation to make things reasonably Gaussian before we do anything else. And then, using standard statistical formulas we learnt back at school, we can build an empirical covariance matrix that links the measured past to the modeled future based on 500 runs of the complex model, the only complex model runs that we will have to do. Here, O is the outputs corresponding to field observations, S is predictions that we care about. Once I've built an empirical covariance matrix that links the measured past to the managed future, I can subject that covariance matrix to singular value decomposition. Once I've done that, I can build a statistical model that does the same job as the complex model in terms of linking the measured past to the predicted future. This surrogate statistical model has parameters here, which I've labelled X, which are just standard independent normal deviates. And it's easy to show that if I take random samples of these statistical model parameters, the relationships that it provides between the past and the future are exactly the same relationship statistically as that provided by the complex model as exposed in the 500 complex model runs that I've just done. The thing is, this statistical model is just a matrix multiplying a vector. It can be done in 1/100th of a second on a computer. So this then can be used instead of the complex model for tasks that would otherwise be complex and error-prone, such as history matching. I history match this model instead of the complex model to constrain predictions so that when I make a prediction with this model, it's a sample of the posterior probability distribution of that prediction. So I now have a statistical model, and my next task is to history match this statistical model against field data in place of the complex model. That's easily done, and once I've done that, these predictions, I can sample the posterior probability distribution of predictions of management interest. Now there's a couple of ways that I can condition or history match this surrogate model that are provided through the PEST and PEST++ suites. Option 1 is to use the PEST PPIES Ensemble Smoother, where prior probability distribution of predictions of interest is morphed into the posterior probability distribution of predictions of interest. In this video, we'll look at option 2, where I first calibrate the statistical model using Tikhonov regularization to obtain a prediction of maximum likelihood. Then I use a little utility supplied with PEST called Post DSI Mod, which provides predictions that correspond to certain levels of confidence with respect to their posterior probability distribution. This is a little more convenient. The behavior of these samples, the behavior of these predictions corresponding to certain levels of confidence is quite regular if done in this way, and also for reasons that we'll see, this way of obtaining confidence levels of predictions works well when we're doing optimization under uncertainty. So, looking at it another way with another set of pictures, I have random realizations of the prior probability taken from the prior probability of anything I'm uncertain about in the complex model, the parameters normally, but it can be other aspects of that model. Undertake a model run for every one of these samples of the prior parameter probability distribution, run the model over the past and into the future. Then, using a utility from the PEST suite named DSI2, I build a statistical surrogate model that takes the place of the numerical model. And that statistical surrogate model is able to make predictions which are samples of the posterior probability distribution of certain predictions that I've made during this surrogate model training process. I then history match or condition this surrogate model on real field measurements to obtain the prior probability distribution of predictions of interest, or using post DSI mod, predictions that correspond to certain confidence levels. So, this is extremely efficient and opens up huge possibilities for making efficient predictions in complex groundwater environments in many different circumstances. But how can we use this to do optimization under uncertainty? I've trained the model to make certain predictions here, yes, but when I'm doing optimization under uncertainty, these predictions will change because every time I do a model run or a run of a statistical model or whatever model I'm using in an optimization under uncertainty context, I'm using a new set of decision variables. For example, a new set of pumping rates. What I do not want to have to do is to retrain the statistical model by running the complex model 500 times every time I want to try a new set of decision variables. Otherwise, it would defeat the purpose of using DSI. Fortunately, there's a way out of this, and that's what we'll discuss next. During this training process, 500 runs of the complex model with different random realizations of the prior parameter probability distribution, I can use random realizations of decision variables. Therefore, the fact that I'm going to be using different stresses when I make different model runs during the optimization under uncertainty process can be taken into account in ways that we will now discuss. And this methodology, where we sample the prior probability distribution of parameters and the prior probability distribution of decision variables, comprises a method called DSIVC, data space inversion with variable control. DSIVC allows us to introduce the efficiencies of DSI to optimization under uncertainty. The method that we're going to talk about was actually introduced in a paper in Computational Geosciences that is on your screen at the moment. It's also described and illustrated in a GMDSI tutorial. This can be downloaded from the GMDSI website so that you can do everything we're talking about yourself. In illustrating the concepts that follow, I'm going to use the example from the tutorial. It's always easier to talk about abstract concepts if we can refer back to a concrete example. And in this case, the concrete example is actually a synthetic example, where we've got an alluvial system here with heterogeneity that has elongate in the direction of the river flow, the new channel, the old channels. It's uncertain. We've got inflow into the top of the model domain, somewhat uncertain. We're pretending we've got some contaminant in part of the model domain and that we're introducing 13 wells to this model domain in the hope that by pumping from those wells we can contain the contaminant, so none of that contaminant reaches the river. The task we set ourselves is to make sure that containment happens with the minimum amount of pumping. So minimizing pumping subject to the constraint that no contaminant reaches the river. This is our constrained optimization problem. We're assuming that we have a calibration data set which is comprised of heads in 15 wells spread throughout the model domain, some of which coincide with pumping wells. So this is our calibration data set. This is what we can use to constrain the uncertainty of predictions that are made by the real model if we used it, or the surrogate statistical model if we use that. And in this steady state flow field, if we do not undertake any pumping and we release a particle in every cell that's contaminated, we can see that all these particles reach the river. And note this channel here and how it is so effective in conveying particles to the river. This will become important later on. So, back to one of the pictures we showed before of how DSI operates. Random realizations of the prior parameter probability distribution fed to the numerical model. The model runs over the past and into the future. The DSI utility from the PES suite builds a statistical model which we then condition, calibrate, history match on past measurements of system behavior, field measurements, to obtain the uncertainty of a prediction we care about, either the probability distribution of that prediction or predictive values corresponding to certain confidence levels. Now with DSIVC things are somewhat similar but somewhat different. In this case, our realizations that are used for training the statistical model include random realizations of hydraulic properties just as before, and also inflows into the top of the model domain because we're not exactly sure of those in this case. They also include random realizations of pumping rates from the wells that comprise this containment system. So if we're going to do 500 runs of the complex model for the statistical model training process, we are taking random values of hydraulic properties inflow rates and pumping rates from the individual wells which comprise the containment system. We run then through the complex simulator over the past and into the future. But in this case, the past is a little bit different from the normal past. The past is what we use to condition the statistical model. Now in this case, the predictions are pretty straightforward. How many contaminants reach the river? And our constraint is that we want no contaminants to reach the river, no particles to emerge at this southern model boundary. But the model also calculates steady state heads at observation wells. These are going to be used for conditioning. What we also use for conditioning is the pumping rates that are actually used to make this prediction. So we use DSI2, that utility supplied with PEST, to build a statistical model that links random parameter fields, random inflows, random pumping rates to predictions we care about. And this statistical model encapsulates the statistical relationships between these, what happened in the past, the pumping rates that we're using, and what will happen in the future. When we condition this model now to make a prediction that we care about, the conditioning data set is comprised of, as usual, measured heads, the calibration data set, but also the set of pumping rates that we would like to use on this particular occasion. Once we condition it on measured heads and the pumping rates that we would like to use when we want to make a prediction, we can obtain the uncertainty of that prediction or predictions at various confidence levels. Now, when we're doing optimization under uncertainty, it is the optimizer that is going to be selecting pumping rates to test. So every time that the optimizer selects a set of pumping rates, the model that the optimizer is actually going to run becomes a conditioning process for the statistical model. The statistical model has to be reconditioned on the selected set of pumping rates every time the optimizer chooses a new set of pumping rates to test as part of its constrained minimization process. So whenever the optimizer runs the model, it is actually conditions the DSI statistical model on the pumping rates that it has just selected. So the model is PEST plus post DSI mod conditioning the statistical model. So this is a little bit numerically intensive. It requires that the statistical model be recalibrated on every occasion of its usage. Now this can take quite a few runs of the statistical model, but don't forget that the statistical model only takes 0.01 of a second to run. So conditioning it may take 30 seconds to a minute at the most. And this is parallelized, even though it takes maybe a few hundred runs of the statistical model. It takes very few CPU resources, very little memory, so on the one computer it can be parallelized 5, 10, 15 times, so this can all happen very quickly. The numerical burden is still virtually nothing compared with that of traditional optimization under uncertainty, where we have to run the complex numerical model maybe a few hundred times on each occasion that the optimization package chooses a new set of decision variables. And let's not forget that if we're doing things the traditional way, the parameter fields we use here have to be samples of the posterior probability distribution of parameters, not the prior, so there's a large numerical burden required to obtain these. So we go from this, if we're doing things traditionally, to this, if we're doing things using DSVC. every time the optimization software chooses a new set of decision variables, the cost is calculated, same as normal, and the model that is run by the optimization software is actually PEST, conditioning the statistical model. The output that we're interested in is the number, in this case, the number of particles that reach the river, or something of management interest, something that that is the constraint in the constrained minimization process. And here is where we get to choose the level of risk, the risks that we're prepared to take. The constraint could be the most likely prediction of the management thing of interest, number of particles that reach the river. Or we could say, no, I want to be very risk averse. I want there to be no possibility of failure. So the constraint here is going to be the most pessimistic prediction of the number of particles that reach the river, or anything in between. So using post-DSI mod following the conditioning process allows us to choose our level of risk as the constraint that's used in the optimization under uncertainty process, so that I can tune that process to the risk that I am prepared to take as I minimize my cost, subject to the constraint that I achieve a certain management objective at a certain level of probability. And that, in a nutshell, is DSIVC. Now, to talk about it a little more, we'll focus on the GMDSI tutorial example to demonstrate its use, and that will make some of the principles that I've just explained hopefully a little more clear. So in this tutorial, as I've already explained, we have an alluvial system beside a river. We're using a structured grid numerical model, but anything that we talk about here can be just as easily done using an unstructured gridded model. 2 kilometers from here to here, 200 columns, 100 rows, cells 10 meters by 10 meters. The simulators are ModFlow 6 for groundwater and ModPath 7 for particles. The model runs over 2 stress periods, both of which are steady state. So my observations, the calibration data set is acquired under steady state conditions, and capture is assessed, or capture or lack of capture is assessed under steady state conditions. I have inflow into the top of the model domain, of which I'm not entirely certain. I've got a fixed head boundary at the bottom of the model domain simulating a river, the elevation of which varies from 15 meters to 10 meters as I go from west to east. The calibration data set, as we've already said, is comprised of 15 steady state head observations. And my decision variables are comprised of pumping rates at 13 wells in and around the area of contamination. The cost is very simple in this case. I'm simply summing the pumping rates. My objective is to minimize pumping rates, subject to the fact that I have complete containment of the contamination. Now, to generate random realizations of hydraulic property fields, I use a utility that comes with the PEST groundwater utility suite named FieldGen2D_SVA. This allows us to generate hydraulic property fields whose geostatistical properties can vary throughout a model domain. In this case, I want the correlation length of any heterogeneity to follow the direction of the river, or the new channel, or the old channels. I want things to be isotropic here, but much more anisotropic here. And when I talk about isotropy or anisotropy, I'm not talking about actual hydraulic properties. I'm talking about the spatial correlation length of any heterogeneity that exists. So, for example, areas of high hydraulic conductivity, I am saying, need to be better connected here than here, in accordance with the depositional environment that gave rise to their existence. The methodology that I'm using for random field generation is one of spatial integration using a spatially variable kernel in the integration function, and I'm integrating random normal variates that are supplied to each one of the cells of this model domain. This method is discussed in the documentation of the pest groundwater utilities and is also discussed in other GMDSI videos. So here is reality, and it's one such random field. We can see spatial correlation of heterogeneity follows the river pretty well. Things are more isotropic at the top of the model domain. Now, I'm using hydraulic conductivity and transmissivity interchangeably here because I'm assuming the aquifer is only 1 meter thick. In retrospect, I should have assumed 10 meters thick. I would have got higher pumping rates in what you're about to see. But it's the principles that matter, not the details. So this is transmissivity, this is hydraulic conductivity. And here are the steady state heads computed using this transmissivity field and a certain set of inflows from the northern part of the model domain. And here's the fate of particles that start in the contaminated area. And note, as I pointed out before, the role of this conductive channel. So to train the statistical model, I run the complex numerical model 500 times. And on each occasion of its running, I select a random set of inflows from the prior probability distribution of inflows. I choose a random hydraulic property field from the prior probability distribution of hydraulic conductivity throughout the model domain, and a random set of pumping rates from the 13 wells that comprise my containment system. So I built comprehensive statistical relationships between steady state heads at observation points, which are calculated during that first steady state stress period by the complex model. These are my calibration data set. Pumping rates from extraction wells, these are the decision variables, which random realizations are supplied in building this statistical model, and I'm building statistical relationships between all these quantities. And of course, the number of particles that emerge from the contaminated area that emerge at the river. These are my constraints. So 500 model runs based on 500 realizations of these components of the optimization under uncertainty process to build statistical relationships between them. The DSI utility that comes with PEST builds the statistical model, which I can now use to perform optimization under uncertainty. So here's the pictorial representation of what we've got. In this case, the optimizer is CMAES-HP. This comes with the PEST suite. CMAES stands for Covariance Matrix Adaptive Evolutionary Strategy. You can find out more details on that by reading PEST documentation, but more importantly, documentation of the original scheme. And in PEST documentation, I point you to the people who invented this scheme and papers that describe it. But this optimizer has had a lot of use over the years in optimization of pumping weights and appears to work pretty well. But as I said earlier in this video, there are other choices of optimizer that I could also have used, for example the PEST PP MOU optimizer. But we're using a global optimizer here. Whenever it selects a pumping rate, we calculate the cost, and then the model that the optimizer runs is PEST, conditioning this statistical model on the measured steady state heads and on the pumping rates that have just been supplied to it by the CMAES-HP global optimizer. The output of interest, depends on my attitude towards risk, as we've just talked about. So the first example we're going to look at is when I decide to be risk neutral. So I'm looking at the prediction made by the statistical model that lies at the center of the posterior probability distribution of how many particles reach the river each time a set of pumping rates are selected by the optimizer. So if I base the optimization under uncertainty process on predictions that are lie roughly in the center of the posterior probability distribution of predictions, that is, if I'm prepared to be risk neutral, if I'm prepared to accept a 50% probability of success or 50% probability of failure, the CMA ESHP governed optimization under uncertainty process tells me that if I pump at 4.68 cubic meters a day with the disposition of pumping according to the size of the dots here, then no contaminant will reach the river at the 50% level, 50% probability level. Now, I apologise for the fact that these pumping rates are a little bit low. I made the aquifer perhaps a bit too thin, but it's the principles that matter, not the numbers in this case. So, I take these optimised pumping rates from my containment system. And in this case, I know reality, it's synthetic. So I take those optimised pumping rates, put them into the reality hydraulic property field, and what I find is that between 20 and 30% of particles actually do reach the river. And they reach it through this conductive channel here. So I was prepared to accept a 50% chance of failure. And because there is something a little bit, it's real, but it's a bit unlikely that we have this conductive channel just to the south of where the contaminant is, then at that level of risk aversion, which is only 50%, and being prepared to accept that there's a 50% chance of failure, in fact, failure happens. So, I have not achieved my goal, my management objective. So let's repeat the process. And this time, the outcome of the model that I'm using as the constraint in my constrained minimization process is the number of particles that reach that southern model boundary at the upper end of the 68% confidence level. So I'm prepared this time to accept roughly a 30% chance of failure. And that's the constraint that I provide to the constrained minimization process that has been undertaken by CMA ESHP. On this occasion, the optimizer tells me that if I pump at 7.05 cubic meters per day with this distribution of pumping, and notice it's less wells that I need to pump from now, then I will effect containment. I will contain the contaminant, no particles will reach the river. If I now put these pumping rates into the reality hydraulic conductivity field and reality inflow from the top of the model domain, in fact, I do have containment of the contaminant. And if I want to be really risk averse and say I want to do optimization under uncertainty, but I'm only prepared to accept a 5% risk of failure, then once again I have success. In this case, the total pumping rate calculated for me by CMAES is 6.83 cubic meters per day, and I have containment. But there's a little bit of a problem here. Why do I have to pump less to have a greater probability of success? Well, that I think comes back to the behavior of ModPath. This is a highly nonlinear problem, not because it's intrinsically a highly nonlinear problem. I think it's highly nonlinear because of the operation of ModPath's weak sink functionality, where a pumping well can go from capturing virtually no particles to capturing many just with an incremental change in pumping rate if it becomes a strong sink rather than a weak sink. But that's beside the point. The process has worked well. And what we found out from this process, that we really need to take account of uncertainty if we are trying to optimize management outcomes, if we are trying to achieve certain outcomes for the minimum cost. To do so without taking account of uncertainty provides no guarantee that we're successful. We have to embed the seeking of those guarantees into the optimization process itself, specifically on account of the risks that we're prepared to take and that way that we then set constraints on the optimization process. And in the present case, well, we can contain this contaminant with a small number of wells to the south, but making sure particularly that we pump to the south and east of where the contaminant is, because to the east there is a possibility of a fast track to the river. So, to finish off, DSI-VC, what are its benefits and drawbacks? Well, I think this has enormous potential myself. It's numerically cheap. Yes, it's complex, but optimization under uncertainty is complex. And there is some numerical work here, but far less numerical work than if we did optimization under uncertainty in the traditional way. And because DSI-VC is based on DSI, it inherits some of the nice things from data space inversion. We can have a complex model with complex hydraulic property fields that don't have to be adjusted. So we can express hydrogeological nuances in as much detail and complexity as we like. We can accommodate uncertainty, complicated prior uncertainty. I also think that the uncertainty intervals that are calculated by data space inversion have credibility, as much credibility as those calculated in any other way, but done at much less numerical cost. There's no need for adjustment of parameter fields, and that saves the risk of bias and it saves the numerical cost hugely. The bad things. Well, it's still a new method, so we've got a lot of work to do to show that it can actually serve its purposes in the groundwater management contexts in which we work. With present software, it's a little bit complicated to set up. That can change with time for sure if people want to use this method. A problem with DSI in general is that you don't actually get to see parameter fields that lead to pessimistic predictions. That's both the strength and the weakness of data space inversion. It's a strength because you don't have to adjust parameter fields. It's a weakness because sometimes it's nice to see what is the aspects of a system that can cause pessimistic things to happen. And perhaps the optimization process suffers a little bit if the relationship between decision variables and outputs of management interests are very nonlinear. But that affects every optimization method that we would choose. So that makes DSI probably no different from any other method. So that's DSI-VC. That's the end of this video, and thanks for watching.